Okay, page 13 of the synchronization notes, and this is section 5, another synchronization problem called deadlock, and the text reference is 11.1. So deadlock occurs when we have a cycle of tasks that are holding resources or mutexes, and they need resources held by other tasks, and those tasks in turn need the resources held by them. So it occurs when there is a cycle of tasks holding resources that are needed by other tasks and waiting on resources held by those tasks. So shared resources such as the classic example is tape drives, not so relevant these days, but let's say files, shared data, I/O devices are guarded by mutexes. So this whole discussion will be framed in terms of mutexes being held. So let's just look at a simple example of this. So we've got task 1 here and task 2, and what task 1 will try to do is acquire mutex A and acquire mutex B. So you'll notice instead of saying wait and signal, I'm going to be saying acquire and release whenever I talk about mutexes. So acquire mutex A, and it needs two things. So maybe these represent two different files, one it's reading, one it's writing, or something like that. So it needs to acquire the mutex for both before it can do whatever work it wants to do, and then it will release both. And the order that we release here probably doesn't matter much. Oftentimes you release in the opposite order that you acquire. Depends on the context. And task 2 wants to do the same thing, but it's been coded so that it acquires the mutexes in a different order. And it could just be a circumstance of what you're trying to do in task 2. So acquire mutex B, acquire mutex A, and these will often not be side by side like that, like there will be other things in between them. Maybe the inner acquire is part of a nested function call, and then it will release. So release mutex A, release mutex B. So let's draw mutex A here, mutex B, and mutexes, their initial value is always 1, and so let's go through what happens here. So say that the control flow, so this is the control flow, is that task 1 acquires its first mutex, and then maybe we have a context switch. So we go up to here, and it's acquired mutex A, so its value is now 0. And then task 2 acquires mutex B, so its value goes to 0. And now task 2 keeps going, and it, I'm just going to put arrows on these. It tries to acquire mutex A, but mutex A is held by task 1, so task 2 is going to block here. So since it's blocked, execution can go back to task 1. And task 1 will try to acquire mutex B. And it's going to block because mutex B has already been acquired. So they're both blocked. They're both holding something that the other wants and waiting on what the other has. So it's a very simple example of deadlock. And unless you've used like a timeout when you try to acquire the second mutex, you're going to be waiting forever. So they'll never unblock. So to discuss deadlock, it helps to use a more abstract representation of tasks, and the representation is called a resource allocation graph. And here is the resource allocation graph for our example above. So this square will represent a mutex, which is protecting a resource. So let's say that's mutex A. And there's only one instance of mutex A, so there's one dot in there. And then the other square here will represent mutex B. And next we have tasks that are represented by nodes or circles. So this is task 1, this is task 2, and in the situation that we had up above, task 1 holds mutex A, so that is represented by a line from the dot in mutex A to task 1's circle. So I'm just going to add text to say what this denotes. So this says task 1 holds mutex A. And we might as well add that task 2 is holding mutex B. Don't need to add the text for that. And task 1 is waiting to acquire B, and the way that we show that it's waiting to acquire B is that the line goes from task 1 to mutex B, and it just goes to the outside of the box, not to the inside. So this denotes that task 1 waits on mutex B, and task 2 is waiting on mutex A. And a resource, so the boxes are resources. A resource can have multiple instances, so maybe you had in the old example multiple tape drives and you had a semaphore and you didn't care which one you had. So you would initialize the semaphore to equal the number of tapes, and you would decrement it as a process took control of a tape drive. So to represent a resource with multiple instances, use multiple dots. So for example, here's a resource such as a semaphore that's been initialized to 2. So a semaphore initialized to 2. So we're going to use these resource allocation graphs in our discussions of deadlock.